Hey everybody. I got a few students who were not able to keep up in class today. Probably a good majority of the students actually. So I thought I'd make a little video, try and slow things down a little bit, and walk through some of the concepts that we were trying to cover. So first of all, this script was really trying to calculate the height and trajectory of a rocket, right? So I'm going to start just by creating a script and saying calculate the rocket height and velocity, right? And what we want to do is set the parameters of the rocket based off of some information that we can collect on some actual rocket equipment. So here we have the ISTES rocket, and I'm going to try to open up that link. Let me just preview. There. And I've already converted the values on here, but you can actually see here's the rocket that we're looking at, right? And it's a small scale model rocket, and there's some parameters here for the length, diameter, and weight. And you can also get all the information on the individual rockets down here, and these are all in the standard class engines. That's where I'm pulling all that information from. So if we want to define the parameters of the rocket inside our script, right, we have a couple of things that we want to have. We have the mass of the rocket in kilograms. I'm just going to call that M. And our mass was 0.0255. And if you prefer writing it like that, then you can do that. You can also put the comment after the mass, and that keeps it a little bit cleaner or shorter as far as the number of lines that you need. And I'm just going to put input all of the rocket parameters. I need to know what the thrust of the rocket is, right? So we called that force. So I'm just going to call it again force in this. In this case, we had a rocket that had a 5 Newton thrust, right? So this is going to be the thrust of the rocket, really the engine, in newtons. We have a burn time, right, which we called the T thrust or T engine in class. And for this rocket, it has a burn time of 0.5 seconds. This is the burn time, the engine in seconds. And then there's also a delay for the parachute, which I'm going to call it T shoot. And this engine is 3 seconds. So delay before ejecting shoot. And we had a V shoot defined as well, although it would probably be better to calculate the terminal velocity based on the drag of the chute. But let's just use this right now of -20. Right, so this is the terminal velocity with the chute deployed. So we have all those defined, and then we also have some parameters of the environment. So we have environmental parameters. So we have gravity, we have 9.81. Oh, that's going down, so I'm going to say actually negative 9.81. Gravity, acceleration on Earth. Don't know if you need to say that, but it's in meters per second squared. And we also have the density of air, which we didn't use in class or didn't really get around to, but and we could say that that is, let's see, I gotta look at my notes. 1.225. This is in kilograms per meter cubed. One thing you want to do is whenever you're using units in MATLAB, you want to make sure that you're consistent. So if you're using kilograms, always use kilograms. If you're using newtons, make sure you're using kilogram meters per second, kilogram meter second squared. So if you're just consistent with your unit system, it's going to make things a lot easier for you. This is here at sea level. And again, this would change, you know, as you went to higher altitude. And that's another thing that you could consider when you're running your code. So I'm also going to have vectors that I'm going to calculate, right? So I'm going to initialize each vector. So I have my index n. It's just my index. I have my time t. And I'm going to note here this is the same as clearing and setting t1 equals to 0. So in class we cleared t and then set t1 equal to 0. But if we say t equal to 0, that's going to make the same value in my workspace as clearing it and then resetting it. So that works just as well. So I'm going to say v equals 0 and h equals 0. And again, if you wanted to, you can keep these in one line too. I like having them all separate. So again, and this is the initial velocity. And this is going to be in meters per second. And this is going to be my height in meters. And then what I'm going to do is I'm going to create a while loop, and I'm going to say while my height is greater than or equal to 0. And I'm using greater than or equal to 0 because I really want to make sure that I'm starting at 0. So I can't say, well, it's greater than 0 because it starts at 0. So that would evaluate to false and I wouldn't do anything, right? I can say, well, that, if I want to be a little more cautious, I can say, well, and n is less than some large value. They use 50,000 inside the book. And that's something that you can put in and then take out if it's obviously not going to be used. And I always like to put the end statement for any loops that I'm going into right at when I make it, so I can keep track of them a little more easier. So this is end while h greater than 0. And really this condition is saying continue as long as the height is greater than 0, or greater or equal to, or equal 0, right? Now I have a few situations here that I'm going to have to deal with. I'm going to have to deal with while the engine is burning, while the engine is off but the parachute is not deployed, and while the parachute is deployed, right? So I can say if the engine is burning, right? So I'm going to say if my t n, actually I'm going to initialize my t and my n here, so n is equal to n plus 1. My index, so I'm going to increment my index. Index n. I'm going to say that Tn is equal to T of n minus 1 plus some dt. In this case I don't have a dt defined, but I can just type it in there. And again, since I'm not using it a bunch of times, it doesn't really matter if I define it here or up here. If you want to have it be easier to change, then it's easier to put it up higher in the code because you can find it quicker, right? we're going to say if Tn is less than T engine, right? And again, I want to make sure that the name here that I used is the same. So I like to highlight it and just check and make sure those colors match up. So that's if the engine is burning, I'm going to say that the force, I'm going to say the total force, let's just say TF, total force, is equal to force minus mass times my gravity. Actually, I already have gravity as negative, so let's just make it as plus. Since gravity is going down, we want that force to be negative, but our gravity is negative, so we just leave it like that, right? Force and mass times gravity, and then we also want our drag force, right? So I can put that in here just as an equation, or I can calculate it before. Let's do it like this, then we can change it later. So okay, drag force is equal to, again, I have 0.5 times my air density times my cross-sectional area, which is one of my rocket parameters, which I didn't include up here. So let's actually add this. So area, let's say the area is equal to pi times the radius of the rocket, which I go back to my notes here on the rocket. We have a diameter of 0.0188 meters. So what we'll do is pi d divided by 2. So pi 0.188, that's the diameter in meters, divided by 2. That'll give me my radius. So there's my pi r squared, the area of the rocket. And this is going to be area of rocket. And then this is the cross-sectional area if you're looking straight onto the rocket, right? So I want the area exposed to drag, really, in meters cubed. And this is going to be a pretty small number, right? But that's okay because it's a small rocket. Times area times my velocity, the current velocity, right? Which actually I haven't calculated that current velocity yet. So let's use the previous velocity. It's going to be a little bit off, but that's okay. Squared. Right, because right now we're on n+1, right? So this is really going to be the drag on the rocket using the velocity from the previous time step. Because we haven't calculated the current velocity yet. We won't calculate the current velocity until we know what the current acceleration is. And then we'll use the acceleration to calculate the velocity, and then the velocity to calculate the position. So our total force here, we have our total force, drag force, plus the weight, plus the thrust, right? So calculate drag. And we're probably going to need drag regardless of which condition. So let's move this out of the if statement. And let's put it inside our while loop. Right? All right. So we have total force here. Let's add a little annotation. Total force equal to thrust plus weight plus drag. It's also, we should probably note that drag is going to go in the opposite direction of velocity. So this formulation is going to give us the drag force in a specific direction, right? So we may have to have something like that says if velocity n-1 is less than 0, so if our velocity is negative, then we'll say that our drag force is equal to negative df. And we'll also make this equal to negative because we want the drag force to be going down when our velocity is positive. So if our velocity is positive up, it's going to go down. If our velocity is negative, our drag force will actually be positive. We'll be negative if it's negative, right? So let's comment that out. Probably gone a little too long without saving and running this. Let's save it. I'm going to put this in my week 11 folder on my desktop here, or on a very hidden folder deep in my desktop. I'm just going to call this rocket. And I want to try and get this to the point where it's just going to work. So let's get the last couple of calculations here, because this is going to run forever unless I have a condition where it's going to fall again, right? So we still got to keep going, even though this is probably a little bit too much to really wrap our hands around at this point. So if the time is less than t engine, our total force is going to be equal to just the force, the mass times gravity, and the drag. And then we'll add an else here. We'll say else the total force is equal just to mass times gravity plus drag, right? So this is free fall. We can calculate acceleration based on force. So our AN, and here I can initialize my A2 if I want to. Acceleration is going to be equal to my total force divided by my mass, right? Because force, acceleration times mass is equal to force, right? Or force is equal to acceleration times mass. F equals ma, right? And then we're going to say that our velocity, n, is equal to my acceleration at time n, right, times my dt, which in this case I have as 0.01. Although again, if I'm going to be using it more than once, it's probably a good idea to initialize that as well. So I'll say dt equals to 0.01. And then right here, I'll just replace this with dt. I'll replace this with dt. And then here I have, this is my change in velocity, right? So I'm going to add that to my previous velocity. So my velocity at n minus 1. Right? And then the equation for calculating my position or my height is pretty much the same thing. We're saying height n is equal to the change in height, which is based off the velocity, the current velocity, times my dt plus my previous height, right? And so this should actually go through and calculate now. So let's try running it and seeing if it works. We got an error. So the following error occurred converting from TF to double. So right now I actually have TF defined as two different arrays. We have TF lowercase and TF uppercase. Let's do TF uppercase. TF uppercase each time. Also, I probably don't want to have my TF display every time I calculate something. So let's fix that. And let's try it one more time. Looks like it calculated. I didn't get a plot out. So I can plot this using the figures over here. I can just add my plot at the bottom here. Let's just add it here. So let's create plots. I'm going to plot my time and height. I'll plot my time and velocity. Right? Actually, let's show you guys an extra function. Let's just do plot YY. This is a double axis plot. And this is nice because we actually see the height and the velocity at the same time. So here on the blue one, which is the first one, right, we have our height, and then on the orange one we have our velocity. And looks a bit different than the previous one. In this case, our velocity is starting off at 20 and then going to 40 and then dropping down. It seems like a rather gradual transition. I think we should have we are accelerating until we get to 0.5, but we should be adding the velocity in small increments each time. So our AN initially, let's look at our debugger and see what this actually calculates. Let's run this again. And we have our vector A, which is currently 0 because it's just the initialized value. And if we step in, we got our acceleration as 186.2. Well, we forgot to add the mass of the rocket, or the mass of the engine. This is the mass of the rocket and not the total mass. So that's one of the reasons we have a big difference there. And then our V, our dt should be 0.1, so we should be getting 18.6 for our first velocity. And then we run through it again, calculating each of the parameters. We get our second acceleration, same as the first acceleration. So our velocity should be increasing linearly. Let's take a look at our velocity. We went 0.01, so we have 0 to 0.18, 0.32. That makes sense. If we continue through, we can actually see all those come out. Oh, it's because I'm looking at my velocity. The velocity here starts at 0, right, and then is going up and then coming back down. So probably one of the biggest reasons we're seeing this is because that our plot here, our velocity when it hits the ground, is actually quite high because it's falling a long ways. It's also falling very quickly, whereas in the previous ones we used the chute to slow it down. And so this one is going to crash land way further out. It looks like it's only going for 1.2 seconds. And that's probably because it doesn't achieve nearly the same height as the previous because we have all of that drag. So it might be interesting for us to look at the different components of the force in this as part of our analysis as well. So let's try doing that. Let's look at initializing vectors for drag. So let's just say dF here, so drag force, we'll initialize it as 0, and then we'll just calculate drag force as a function of our index. Right, and then we can actually see what our drag force looks like for each one. Of the form TF is equal to we've got to index our drag force here, so we need to do drag force N. We don't want to use the whole array, we just want the current value of the drag force. And then the rest of these are all constants, they're not changing. Let's try that one more time. dF is equal to negative, dfn is equal to negative dF of n. Alright, so let's look and see, we have our plot again, back out. Let's look and see what our drag force looks like. It should be proportional to our velocity. So I'm opening a new figure window, and I'm going to plot my drag force. So this is my force and drag over time. You notice here it starts off at 0, it peaks when I have the velocity peak in the negative direction, right? And then it continues going down. It looks like one of the things that I forgot to do here in my free fall, I have the mass times gravity, and then I have plus g, which really what I wanted to have there was plus my drag force. So I forgot to add my drag force when we're falling. So going up, it had the drag force. Going down, it was just falling super fast. There you go. And that looks a lot more appropriate based on what we were seeing before. So we have the acceleration the parabolic motion, and then it kind of comes down. It actually looks like it reaches terminal velocity before it hits the ground, even without the parachute, although it is coming down quite fast, right? Looks like negative 30 or so meters per second. So now we're working. Let's go ahead and add our condition for the deployment of the chute. So here we'll say else if Tn, right, is, actually we wanted to make this our statement here. So we're in free fall before our T chute. So in this case, our time is less than the time at which the chute deploys. We're in free fall. And then if that's not true, that means our time is greater than the T chute. And so we'll set our drag force to something higher, or we can just use a different calculation for our velocity, right, or for our acceleration. But for this, let's just say, let's recalculate drag force, and we'll just say our drag force, dFn, right? And I'll look at the diameter of the chute. So what's a good diameter for a chute? So don't know what that is. Let's see if we have anything on here as far as the parameters of this parachute. Looks like this one actually doesn't have a chute, it just has a streamer. Well, let's just make something up then. So let's say it has a 10-inch chute. So 10 inches would be 0.25 meters. So let's calculate our area as 0.25 squared times pi. Actually, that would be a 10-inch radius. That's probably too much. Let's just put 0.1, right? So a significantly larger cross-sectional area than our original one. We also forgot the drag coefficient here. Let's just put it into our code. So 0.5 times, a good coefficient for the rocket would be 0.2. A good coefficient for the parachute would be 1. So we just do times 1, but we just leave it like that too. Let's see what that looks like. Looks like I'm replotting on the same axis. I have overlaps here. I'm going to close this and run it again. It looks a little cleaner now. So our velocity is coming down, and the final velocity looks like it actually got higher. Oh, because our drag force is negative here, and we want it to be positive if it's going down. Let's copy this out. I'll paste it again. I don't know for sure which direction the velocity is going, even in this last condition. So I still have this else if statement. That recalculate. Looks like when I replace this drag force here, I get rid of my recalculation of my TF. So we still need to calculate what the force is to be able to use that drag force. And really what we probably should have done is just multiplied our drag force times a constant, because we're only changing the cross-sectional area. So let's do that. Let's just say TF is equal to mg plus 10 times df n. So a much higher drag after the chute is deployed. So now we can see that our velocity decreases sharply after that chute is deployed here, right? It's actually before we reach the maximum height. So we curve down and then it comes down and it finishes at a much lower velocity than we had previously. So I hope that's helpful in kind of understanding how some of this stuff works and how we can code out some of these examples. If I wanted to, I could also change this into a function that does all this with a smaller number of inputs, right? So if I wanted to make a function for max height for this rocket, right? I forget what this rocket was called. It was called the... Oh, do I have it in my presentation? The High Flyer. Right, and then I could give it the engine parameters, right? So engine mass, the thrust, burn time, what should we call it? Force was my thrust. Force, T engine, and T chute. And it actually looks like inside here I never did add the mass of the engine to this mass. So let's actually add engine mass. So I have engine mass, force, the thrust of the engine, the timing of the chute, into this function for my High Flyer, right? Now I could actually run this for multiple different engine parameters, taking these guys out here, so I don't need this T engine, T chute, what else? Force. Right, so now each of those is defined inside my function call. I'm going to save this as High Flyer because the function name has to be the same as my variable name. And I can even run this in a script for each of my rockets, right? So I could say figure max of A8 3, and we could say High Flyer of the engine mass. In this case, if we look at the charts, the initial weight of the A3 is 0.0162. It has a average thrust or force of 5 newtons, which is what I was using before. It has got a thrust or burn time of 0.5 seconds, and it's got the parachute delay of 3. Right? So let's save that as rocket compare. If we run that, we get our chart out for that rocket. Input. Oh, I never actually calculated the maximum height. So we found the maximum height, which I just did the max height of h. So I'll say max height is equal to max of RH. Right. So I'll save that again. Go back to my code. So again, I get the figure, right? And I get the max height of this. Maybe if I unsuppress it, we can see that a little bit easier. Right, every time I run this, I'm getting a new figure. This one gave me a max height of 124 meters. And actually, we can make this a little bit cleaner still by doing clear all, close all. So you'll see. Let me give this a name. So the name of this figure is A83. And then let's look at a couple other engines as well. So let's look at the B6. Let's look at the B6-4 because it seemed like we needed a longer delay on our time. So the B6-4 has a burn time of 0.8 and average thrust of, let's see, it's got a total impulse of 5. So it's going to be 5 divided by 0.8. And it's going to have a delay of 4 seconds. And it has a total weight of 20.1 grams. So 0.0201. Yes. And then let's do it again for an even larger motor. So let's try I think the biggest motor that this rocket is able to take is a C6-7. So I don't see the 6-7 on this chart, but I see the 6-5. So let's do that one. It's got a total impulse of 10 Newton seconds. And it's got a burn time of 1.6 seconds. 1.6. And it's going to have a delay of 5 seconds. So this is the C6-5. Let's run that and see what each of those looks like. Well, we got everything. This is our B6-4 and our C6-5. So there's our C6-5. We have our B6-4, our A8-3. You see we get a maximum height of about, I don't know, 100 and, wow, this is like our command window, 124 meters for the A8-3. For the B6-4, we get a maximum height of 293 meters. And then for the largest engine, the C6-5, we're getting a maximum height of 598 meters, which is about the 1,500 feet that they claimed that rocket would achieve. I don't know how stable that rocket is with that motor in it, but that's a different issue. We're still not accounting for the variability of thrust over time. So the motors don't actually produce the same thrust the entire time. We have a gradually increasing thrust that then peaks and then goes down and is reasonably constant for a period of time. We're not accounting for the change in mass over time, so these rockets are going to get lighter as they burn through a propellant, especially for the C6-5, the larger engines. And we're not accounting for the density of air, so the air is going to get less dense as you get higher up. And when you start getting to thousands of meters, or hundreds of meters even, that will be an effect that you could account for. So I'm hoping that helps you guys out a little bit. If not, then I'm sorry I wasted your time. See you soon.